I'm Bhavidhir V. Bharadwaj. Welcome to episode 53 of Genesis of Tomorrow. The following is going to be conversation about quite a few main things actually, particularly micro-electromechanical systems, MEMS as you call them, analog circuit designing, quantum computing, sensing, and a little bit of machine learning and AI as well, especially the physical AI side of things, robotics, you see. And we'll cover a lot many other tangents as well, depending upon where the talk takes us, with Dr. Diego Emilio Serrano, who has got his particular background with micro-electromechanical systems. And he is a science and tech advisor at DARPA who did his PhD in electrical and computer engineering from Georgia Tech. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. There was quite some tasks to actually
Okay.
converge upon where to start it, so,
hmm
because there are just so many things. But
hmm
in our previous talk, you stated something, and so quoting back that verbatim of yours to you, you stated that people who are trained on fundamentals tend to think mechanistically,
hmm
right? And it was a very subtle thing that you just mentioned during another conversation that we were having about other things, a plethora of things actually. But let's really start from there.
hmm
Firstly, why do people who are trained and think in fundamentals tend to, by extension, think mechanistically, what it means and what implications does it have?
Hmm. Yeah. Maybe you can give me a little bit of context on when this came up.
Okay.
Yeah. I'm not quite sure. In one context, we were discussing
Mhm,
fundamental
mhm,
and
mhm, mhm.
mechanistic thinking. Um,
The idea about people and thinking in general, how
mhm,
every individual thinks and sort of goes on about carrying out cognition, or cognition carries out subjectively in each and every individual, that varies from individual to individual, right? When you talk about people like us who are so on a day-to-day basis connected with systems thinking, there's these physical theorems, proofs, sort of so is and so isn't distinctions between systems.
mhm,
We often umpteen times are susceptible towards boxing our own perspectives and perceptions to what these laws per se may dictate. And at a physical level, it's completely fine. But when you are trying to find out different approaches or go on about a systems thinking way to solve some kind of problem, it may become a hindrance, a heuristic that may block you from reaching out to avenues that may be novel in their pursuit. So the context
hmm,
primarily being people like us who are relatively more inclined towards thinking into these boxed systems or
hmm.
with this structured logical approach. How can we not maybe box our thinking whenever we are trying to explore new avenues?
hmm Yeah. Okay. So maybe let me take a step back and try to see if this is what we were discussing the time I mentioned this, and is, you know um, there are many scenarios in which you pick a particular subject to study, and you get so into it and so involved with it that sometimes it becomes difficult to think outside of the box, right? And that um, just comes with a particular job. Like, let's say you're a circuit designer, and your day-to-day job is just to work on biasing transistors and building these complex systems. And sometimes it's difficult to pull yourself out of that and see, for example, the bigger picture of what you're trying to accomplish, right? um, and you ask, well, how can we avoid falling in this trap of always just having this very traditional way of approaching problems? And I think that the solution to it is to try to diversify the things you try to focus on, right? So, in your day-to-day job, yeah, you might be a circuit designer, or, a physicist working in the lab, but, on the side, you should try to explore other fields and other branches of science that might bring a different perspective of how you approach a problem, right? Now, I don't know if this was what you were referring to, but with your description, it seems to fit, what I see as, getting too linear in the way you think about a particular problem, right? Um, and I think for me that has come in handy in many situations where I I've been lucky enough that I find many different fields interesting, and I try to pull from each of them new ideas and try to apply them to a particular problem I've been working on. So,
It ties in closely to this. Oftentimes, what the younger folks nowadays may be facing is a challenge more often than not, being what exactly should you as a young engineer, an avid scientist, or somebody who currently maybe is in their undergrad or early years of their master's or PhD, how exactly should you think on about carving out your career? Because uh, traditionally, this sense of career becomes a monolith that you you get through with your high school. If you want to pursue college or not, that's one nodal boolean thing that you decision that you want to make. And then once you make that, okay, yes, one college, fine, you carry out 3 4 years, you decide you want to go into masters, PhD, whatever, all of it converging you towards this one singular description of what you want to continue to do for the rest of your life. But in today's purview of the world, it's increasingly sort of incumbent to not have that monolithic view of a career per se, because there is just so much for you to do, to learn, and to explore. And as extension, why it's the right question to pose to you, because you yourself have firstly a strong background in the STEM area, but after that, through self learning, been able to explore and build a decent amount of knowledge, a foundation of these different knowledge bases.
hmm.
So, what exactly should the young student today think about in terms of career?
Yeah, so if I were to give anyone advice, is I would focus on two things. One is, try to pursue uh, something that you're passionate about. Now, of course, that doesn't always work, and I'll give you an anecdote that
Mm-hmm.
might relevant here, and is, when I was in high school, um, I started learning about physics in the last few years of high school, right? Senior year and so on. And, I decided that what I really wanted to do was study physics. So, I told my parents, but they were going to pay for college, and they said absolutely not. I'm originally from Colombia, and in Colombia, the career path for a physicist is very limited. So, I now live in the US, but back then I didn't know I was going to end up in the United States. So if you pursue a physics career, you're probably going to end up being a professor at a university, and those positions are limited, and it limits your options, right? So they told me absolutely not. So I decided that then I'm going to try to be an engineer, and I'm going to pick the engineering degree that has the most amount of physics to try to, pursue that dream of learning about physics, but keeping my doors open to other possibilities. So those are the two things I would suggest is, try to pursue your passion, but when it's not possible, be flexible and try to, adjust expectations without trying to without getting too frustrated about the outcome, and make the best out of it, right? So the other thing is that people, we all think we're all so busy all the time, and in many parts of your life that is true, but if you really find something interesting and you can pursue it as a career, make it your hobby. And I've done that most of my life, or tried to do that most of my life. And it's, okay, well, I pursued an electrical engineering degree. Well, you don't learn any quantum mechanics when you start electrical engineering. Well, I just did it on the side. I try to, just teach myself and learn about it. And, it was not easy, especially back then, because the resources were limited. But nowadays, I mean, there's so many, courses and videos and material online that you can, teach yourself pretty much anything. I wouldn't say everything, or, you can't, it gets harder the more complex the subject is, but I think, there's a vast amount of information out there that can at least set you in the right direction to try to learn about something on your own. It gets harder when it's applied. So, if you want to be an experimental physicist, and you need this very sophisticated equipment to really get hands-on experience, that of course gets really difficult, right? But at least, if you want to learn the fundamentals, you can do it nowadays. So yeah, I mean, if I were to give advice to someone, is, try to pursue what you want to do, but be flexible, and, try to find a way to get as close as possible to that dream of yours, right? And, the third component will be, well, you also need to think about, the market of opportunities, right? You need to make sure that whatever you're pursuing is going to set you up for success in one way or another, right? You don't want to be in a situation where you study something that maybe is you end up in a saturated market, and then you don't have a lot of choices, or the competition is too high for you to get an opportunity. Now, that's where you need to decide, well, am I at a level where I think I can compete and get a good opportunity, or maybe the market is so saturated that it's just not worth pursuing that path. So you need to readjust and try to find a slightly tangent approach, right? So yeah, you need to also try to gauge your level of expertise compared to others, and how do you navigate the market of opportunities as well. So that's not easy to do, but I think with time people get better at it, and it's something that as an early graduate, or early on your studies, you might want to consider. So yeah, but that goes back to that flexibility, right? If you're passionate about something, you see that the opportunities are limited, well, try to stay close to what you want to pursue, but be flexible and adjust so you can get to something that will get you, will set you in a path for success.
And sort of each and everything that you try to learn, each and every new aspect of a new field that you try to get yourself familiar with, it eventually leads you to develop this unique set of stack which becomes unique to you and actually in some way may dictate your distinct value in the job market. Because uh, a person with X skill plus YZ in alpha may not be existent from that particular background. Like you did your PhD in electrical and computational engineering, right?
That's
But
right.
then
Yeah.
and you then went on to work with the MEMS, right? Particularly
Mhm.
in analog circuit designing. But along with that, you picked up on quantum computing a little bit, sensing, learned about that here and there, and also machine learning and AI.
Mhm.
Now that, and then I'll come on to this. You also try to do projects, open source contributions to Qiskit here and there, other things. And that sort of creates this, carves out this unique portfolio of the individual that Dr. Diego is and his sort of skill stack. Even if he has a formal background in XYZ, he has got this things that he picked up along the way, which becomes valuable eventually, I think.
Yeah,
And
and more than building a portfolio is when you pursue, and this goes back to the first question you asked it, when you try to branch out and learn about a wide range of subjects, it really changes the way you think about problems in a particular space, right? It it's not so much about saying I know about X, Y, and Z specific topic, but also building this habit of picking up different subjects quickly and efficiently, right? So learning about having that ability to pivot and learn something new without having to spend years and years trying to become an expert, right? So you know uh, this might make it sound like that's the reason why I do these things. But honestly, the reason I learn about all these different subjects is because I just find them interesting. So more than trying to build a portfolio, and this ability to learn about things quickly, I do it just because I find them interesting. Now, what you just mentioned are byproducts of doing that, right? From my point of view. So yeah, I mean, I think building that curiosity, it's it's important, but it's also good if you enjoy it, right?
moving deeper into it, firstly, uh, micro-electromechanical systems. What
Hmm.
MEMS are, talk about why this design forces you, what this design forces you to do, resonators, modes, Q factors, non-idealities, like
Hmm.
anything and everything that you need to relate to a person who is turning in for the first time towards understanding what this particular tech stack particularly is. What
Hmm.
is it?
Yeah. Yeah, that's I think that's a good place to start because looking at other people you've interviewed, I think your audience might be more on either the computational side of things or the quantum computing space. I think my background is a little bit outside of the subjects that you typically cover. So it's good to maybe start with a simple explanation of what micro-electromechanical systems are and why they are important, right? Maybe people are familiar with microelectronics. So microelectronics are circuits that you design and then fabricate um, in a large amount using batch processing. So basically, all the devices or components that go inside your phone are microelectronic components, or not all of them, but most of them are microelectronic components, where you have millions, if not billions, of transistors in a single chip, right? So you have this process of fabricating multiple devices by using a series of steps where you end up with an interconnected system that performs a particular operation. So, for example, the CPU does all the processing, let's say on your phone. The power amplifier for the RF system is responsible for taking a signal and making sure it's conditioned to be sent through, the RF domain, and so on. Now, micromechanical systems are very similar, except that instead of building just electrical or electronic components, you're building also mechanical devices. But you use the same fabrication techniques used in the semiconductor industry. So, you start with, let's say, a silicon wafer. You deposit a layer of an insulator, and then some other semiconductor, let's say polysilicon, and then you etch it in a way where you can construct devices that are free to move. So you etch out the insulating layer, and then you can have this miniaturized devices that have mechanical degrees of freedom. So once you have that, you can do different things. So one of them is you can build an accelerometer. So once you
Mm.
have a proof mass that can move as you accelerate, let's say you have this component inside your phone. So as you move the phone, then this device can sense acceleration by measuring, for example, the change in capacitance with a fixed portion of that design. So you have a mass that is free to move, and then an electrode that is fixed in space. And as it moves, you can change that change in distance by measuring the change in capacitance generated by the motion. And with that, you can do all sorts of things. So, for example, you can, as you rotate your phone, you can detect where the gravitational field is pointing, and then the system will rotate the screen, right? But these devices are used in more than just consumer electronics. So, for example, in the automotive industry, each car has tens of these devices for all sorts of applications. So one of them is for safety. So when you're in an accident, the device that senses the deacceleration of a crash is an accelerometer, and that triggers your airbag. Or you can have gyroscopes, which don't measure linear acceleration, but they measure angular velocity or angular rotation, right? So a gyroscope works in a similar way to the accelerometer, but it's a little bit more complicated. You have a proof mass like the accelerometer that can move in a certain direction, and you excite it into oscillation. And then when you rotate the device, then that oscillation, part of the energy that you have stored in that oscillation transfers to motion in an orthogonal direction. So if the proof mass is vibrating in the x direction as you rotate, then you're going to have some amount of displacement in the y direction. And that amount of displacement is proportional to the velocity of rotation. So you can detect that rotation by then measuring a change in capacitance and with electronics amplifying the signal to know how much how fast you're rotating your device. And going back to the automotive industry, for example, you can use these devices to measure if, for example, you're in an icy road and you start turning the wheel and your car is not rotating as you turn the wheel. Well, there's a gyroscope that is telling you, hey, you're rotating your steering wheel, but the car is not rotating at all. Change the speed of the tires to adjust and send the car back in the right direction. So, but again, these components are used in all sorts of applications. I mean, modern drones wouldn't exist if you didn't have accelerometers and gyroscopes. And there's many other applications. You can also use these components to implement filters for RF communications or oscillators to generate very stable timing references, because the quality factors or the ability of these devices to store information, to store energy, is much higher than what you can get with just pure electronic components like a capacitor and an inductor. So this is what I've spent pretty much all of my career working on, and it's an interesting field because it requires a combination of mechanical engineering, electrical engineering to understand understand or design the electronics that condition the signals so you can amplify them and then send them to a processor to make a decision, and other fields of physics. So for example, you need to understand the loss mechanisms that affect this device. So you need to understand a little bit of fluidics. So how if you have a resonant device that is vibrating, how does the air around that device cause the oscillator to lose energy? You need to understand how does that couple with its surroundings. So for example, how much heat is internally generated and how much of that vibration is turning into heat. So it's a very interesting field in that you combine many different aspects to design a device. So for example, microphones today, the ones that go in your phone are designed with are implemented using MEMS technology, and what you need to do to design a microphone is now make a vibrating membrane respond very well to just the frequencies of the audio spectrum, right? But reject everything else. And you need to make it robust enough that when you drop your phone, it doesn't shatter or fall apart, right? So it's a multi-physics type of problem that you need to solve to turn these ideas into a full product.
Mm. Tying that towards analog circuit design, or maybe let's start with circuit design in general. Uh, how, mentioning about MEMS role and particularly this aspect of automotive industry and drones as such, all of it by extension then does bleed into the entire aspect with the proliferation of robotics and physical AI, autonomous
Mhm.
systems, physical autonomous systems. All these algorithms or algorithmic intelligence that we are designing, the objective that we are trying to achieve by definition itself is incomplete if we are not able to materialize into these robotic physical AI systems. And trying to again put into better perspective the significance of such traditional facets of engineering, may it be MEMS, may it be circuit designing, trying to explain how exactly do all these different features of engineering, traditional engineering, fit into the current bleeding edge work being done with AI and autonomous technologies. How does it all tie up together?
Yeah, it's a very interesting and timely question because the way I think about it is these MEMS components are the gate that they're what connects a computing system with the real world, with the physical world, right? So they're just like our sensing systems. So they're the eyes, the ears of a computer or a robot, right? Um, the question is, once you have designed a very accurate sensor, what do you do with that information, right? And that's where the algorithms layer comes in. And many of these algorithms have been around for a long time. So, for example, in the space of inertial navigation, which is taking information from an accelerometer and a gyroscope, how do you tell, let's say, a car or a drone where to go? So, if you think about it, if you have an accelerometer, you're getting a signal that is proportional to acceleration, right? Well, if you know the starting position of a system, you can take that acceleration information, and if if you calculate after a few seconds where the system is, well, you take the acceleration and you integrate it twice, and you get the displacement, right?
Displacement.
So you can use an accelerometer to track the displacement, and then you can use a gyroscope, which measures how fast you're rotating, to calculate where that object is headed. So if you know how fast you're rotating, you integrate once over time, you get the angle where you're pointing at, right? Now you can take the problem with this is that when you do this double integration for the accelerometer and this integration for the gyroscope, you're not just integrating the signal of interest, but you're also integrating the noise. So these
Mm.
components are very, very noisy. And that noise accumulates over time because you're summing it up as you're integrating. And with the accelerometer, you're integrating twice. So that let's assume that your component is not moving at all and you're performing this integration and there's noise. Well, then from the computer's perspective, it seems as if you were moving at a certain rate over time.
Yeah.
So you need first, very good sensors to minimize this error, but also a good algorithm that can compensate for it. So one of the most famous algorithms that has been around for a long time is known as a Kalman filter. So a Kalman filter is a predictive filter that takes as an input information from different sensors. So it could be an accelerometer, a gyroscope, maybe a magnetometer, or you can incorporate, for example, GPS information. So GPS can give you precise information about your location. And there you're not integrating, right? It's not giving you acceleration information, it's giving position. But obviously the GPS also has errors because you can only detect or the position of an object with so much, with a certain level of accuracy. But by combining the information from all these different sensors, a Kalman filter provides a better prediction of the position of the drone or the car more accurately than if you don't have this algorithm incorporated in it, right? Now, these systems have been around for a very long time, but then the question is, well, can AI do a better job, right? Can we incorporate machine learning or AI techniques to improve the performance of the sensors? So that's an interesting area of exploration, but there's a problem, and is that, for example, in the case of drones, it's very difficult to deploy large AI systems to perform inference because you have limited size and a limited amount of power consumption that you can spare to perform the computation. So there's been this emerging field known as tiny ML or tiny machine learning, where you try to implement these techniques that we see in everyday AI applications like ChatGPT or image generation and so on, but where you limit the amount of power consumed by the system by doing, for example, quantization. So instead of using floating point numbers, you try to limit that to be only integers. Or if you're implementing some sort of neural network, you do dropout. So basically you purposely prune some of the nodes that contribute the least to the inference process. And there are tools to do that. But the problem with this is that you always pay a penalty in accuracy, right? So your system is not going to be as precise as what you would get if you could run this in a server. So, another option is, okay, well, maybe you don't perform the computation locally, you send that to a server, and then the server sends you back some of the information from the inference. But that has all sorts of issues, right? It obviously adds a delay and how fast you can respond. So if you have a drone trying to navigate and there's turbulence and heavy winds, and you're trying to do a prediction that runs on machine learning, and you're sending that back to a server, maybe you don't have enough time to respond. Right? So people have started to explore a different avenue, and this is relatively new, and I don't think there are a lot of let's say, practical demonstrations. These are more of they're more at the research level, or the tried in a lab, where what you implement is what is known as a physical neural network. So instead of running your neural network on a CPU or a GPU, you try to implement a neural network in a physical system. So that could be, for example, MEMS components, or it could be an optical device, where instead of having the weights of a neural network stored in memory, you are changing the physical aspects of a device to perform inference. So, for example, you could have a mechanical system where you have several couple oscillators, and you can change the stiffness between the oscillators, and you can do this electrically. You can change the effective stiffness that couples these oscillators to change how the system reacts to a given input. And those springs and their stiffness are the weights of your neural network. And you can do this with also analog circuits, so where you have a mesh of resistors, and then you tune the resistors to be the weights of your neural network. And what you can do is, well, if you need to either store this information physically, so you need to change those resistors and make sure that they stay that way when you perform inference. And if you want to retrain, then maybe you do need to do that. Let's think of, for example, a drone. You need to do that when you have the drone in a base, and then you reprogram it. Or you can send a new set of parameters wirelessly to reprogram it. But then once it's programmed, maybe you can keep those parameters for a long time. But this has also some limitations that people are still trying to figure out. So one of them is that to perform training on this type of neural networks, if you think about the conventional way you do training is with backpropagation. So you need your physical model to also be differentiable if you want to train this on the device itself, right? So you need to be able to, run your forward step and then your back propagation step. But how do you do this if the device, how do you calculate the derivatives to reassign the weights and make the model converge, right? So not all physical models are differentiable. So there are two solutions, and one is try to construct a physical system where this can be done. The other option is you can perform the training not on the device, but on a twin model of the device on a computer, so in simulation. So you have a simulator that matches as close as possible the real system, and you train it on a local computer, and then you can perform the math to know what the derivative needed for backpropagation will be. You calculate the weights, and then you send the weights to the device. And to do this, you can use as a tool. So what I'm discussing is known as physical neural networks, or PNNs. But to train them, you can also use this technique called physically inspired neural networks, or PINs.
PINs, yeah.
Where if you have the twin model of your physical system, what you can do is not only have a cost function that depends on the difference of what your output is with respect to what your, let's say, your label is, or the right output for a training data set is, but you can also include a penalty function that follows the physics of the device, right? So that's another alternative. But ideally, what you want at the end is to have a system where you can train this in situ on the device itself. So try to construct a physical neural network that is physically differentiable as well, so it can be trained on the device. So yeah, so it's an interesting avenue of research, but it's still, I think, a lot of work to be done. But and what I gave you is just one example in the navigation space, but there's all sorts of different examples in communications and thermal systems and so on.
Two matters of discourses particularly. First one being, as we discussed about how these different approaches may inform the development of AI or autonomous systems, physical autonomous systems, robotics, so on and so forth. How currently is and how potentially will AI and machine learning be utilized to inform better development of itself through the means of these approaches? May they be using MEMS or circuit design, so on and so forth. So instead of MEMS and as we discussed, then we talked about pins, we talked about this physical layer of neural networks. They being utilized to creating better
Mm-hmm.
autonomous systems using AI, algorithmic AI, to better define or some way, shape, or form be able to better execute tasks of the said different approaches that we discussed, to then be able to better carry out development in the field of autonomous systems. So, sort of a feedback loop, some way.
Yeah. So um, let me know if I understood this correctly. So how can we use the tools of machine learning and AI to improve the way we design the systems, right? Or design the sensors. So
Yes, yes.
um, so yeah, this is an area that I think there's been a little bit of work done, especially in the RF domain.
Hmm.
So and more specifically for electromagnetic components. So if you look at how RF systems are designed, you need all sorts of different filters, and one of the ways to implement filters is by using just strips of metal that you design as transmission lines, and at given wavelengths you can change the shape and length of this microstrips to perform the function of a capacitor or an inductor at that specific frequency, to create filters with different shapes. So for example, you want to have a bandpass filter with a certain center frequency and some given bandwidth, and then you want a notch filter at this other frequency, and then you design these components that in many situations end up having this very interesting shapes to them, which in many if not in most cases, are empirical. So basically, a designer goes into a simulator and tries a few different things, and following the results of the simulation, you start changing the shape. And if you look at pictures of these things, they have very, very interesting geometries. Well, you can take a database of filters that have worked and the frequency response of these filters and feed it into an AI system or a machine learning system, and constrain the parameters, and then try to have it design the shape of a filter that meets certain criteria. And I've seen a couple of papers on this, and it's interesting. You end up with shapes that you've never would imagine to come up with. So the AI model basically figures out an optimal way to design a component that meets certain specifications that possibly for a human designer would have been very difficult to do. Now you can do the exact same thing with MEMS devices, so mechanical components. So if you look at the shapes of a lot of these resonators, they have very interesting geometries too, because the parameter space is really large. So you're trying to optimize for a given frequency of oscillation. You have constraints on size for a particular product. Since these devices need to be, as I mentioned before, you have a layer where you have the moving structure, but underneath you're going to have a different type of layer that you need to etch to release it. So there are fabrication constraints on certain release holes that you need to add to your design so that the etchant can completely release the structure. You have also critical dimensions that need to be met so that this can be fabricated in a large wafer. So there are process variations that you need to account for, and you're trying to isolate the structure from its environment. You have a wide range of things you need to worry about. So as a MEMS designer, you build an intuition for what are the things that you need to optimize for, and you run simulations and you try to adjust the geometry to meet all the specifications. But in many scenarios, you end up compromising and having to balance things out. Well, you can now try to feed all this range of limitations to an AI model and have it design the geometry, the most optimal geometry for your application. I haven't seen. I saw something many years ago along these lines before machine learning really took off, or the AI craze took off. But it was very limited back then. I think the systems, there was not enough compute to do anything too big. So it was just optimizing over two parameters, let's say. But I think it's an interesting area for people to start exploring again, and see if AI can help you design this mechanical components for better performance. You can see this happening specifically in the area of filters. So we discuss, the example of microstrip electromechanical filters, but there's also acoustic filters that are, very prevalent in a lot of RF electronics. And you could do the exact same thing. You could you could run it through an AI model to try to find a good geometry for a particular application.
That was certainly a very intriguing thing that I want to look more into. I wasn't aware of that applicative area particularly. But moving on to something else that you wanted to talk about was some misconceptions about that people generally harbor about quantum computing and quantum, the entire area of quantum in general, that is very hyped around nowadays. You know, it certainly, I mean, a common denominator happens to be that, okay, quantum is not the pixie dust that will be able to do each and everything or be able to be utilized into each and every facet that you want to. But again, in terms of these misconceptions, where would you want to start? From the most prevalent ones to the most interesting or the most seen ones?
That's yeah, that's a quite a change in subjects, but yeah, let's see where can we start. So I think yeah, quantum computing is interesting because it's it's an emerging field, and I think there's a lot of people trying to make it seem like it's not. That is a it's way ahead of where things are. And I mean, you can see something similar in the AI
Yeah.
space where
Yeah.
there's a lot of hype, but um, I would say that quantum computing is not at the same stage where
Mm,
we're seeing AI being, right, because
mm,
for in the case of AI, there are concrete applications where you see the system doing something useful, right? So, I mean, this is undisputably way ahead compared to quantum computing. Quantum computing, there's a lot of speculation on what you can accomplish with it, but there are no true demonstrations of a practical application, right? So I think that's one of the main misconceptions, and you see all over the place. Oh, this demonstration was the Chat GPT moment of quantum computing, and I mean, come on, no
mm,
way.
mm,
You can't make the comparison. It's yes, we've seen some results that truly demonstrate that quantum computing can perform certain tasks that it would take an impossible amount of time to do it on a classical device. But these are all contrived examples. There's no real demonstration of something that you could present as, let's say, as a business case and say, okay, I've demonstrated this. This is my product. Uh, you know, either pay for the service that I will provide you, or buy a few of my quantum computers so you can do it yourself. There's no such thing yet, right? Now, I don't want to come across as a quantum computing skeptic. I am very pro quantum computing. I think it's a first of all, it's the most interesting field. I think it's out there from at least from an engineer's
mm,
perspective. I
mm,
think it's super interesting. But I think there are so many different levels of misconception that I think it's going to take a few years to try to resolve. So you can start, even just from the most basic level.
mm,
So one of the things I enjoy doing is I spend a lot of time trying to, for example, go into quantum computing stack exchange and see what people are asking. And these are more practical questions, right? This type of website is more like, oh, I'm trying to run the simulation. This is not working. What's the problem? There's also very theoretical questions. But when you start looking at the confusion or the different things that confuse people are just getting started, you start to see that there might be a problem with the way certain things are being presented in the most basic introductory courses, for example. And maybe I'll give you a couple of examples of different levels of complexity. So let's take Grover's algorithm, right? So Grover's algorithm is usually presented as a series of steps that allows you to search through an unstructured database and find one of its elements in quadratically faster than what you can accomplish with a classical algorithm. So for example, if you have, the typical example is, let's say you have a phone book. So in a phone book, you have the names of the people in a particular town organized alphabetically, right? So the first entry is, the someone with their last name starting with the letter A and first name starting with the letter A, and then you go all the way down to the letter Z. And you're interested in finding a specific phone number. So you're not interested in finding what phone number a certain person has, but you're interested in, you have the phone number and you want to find who's the person who has that phone number, right? Well, the phone numbers in that list are completely random. They're not organized, right, in any specific way. So classically, all you can do is just go one by one, checking which person has this phone number, right? So if you repeat this process many times, on average, you would need to, let's say there's n entries. You end up needing to search the list n over 2 times, right? So sometimes you get lucky and it takes you less than going half through the list. Sometimes you're unlucky, it takes you, you need to go past half of the list. So on average, you end up having to scan the list n over 2, right? Well, Grover's algorithm is usually presented as, oh, you give me this phone book and I can find that phone number in square root of n, right? So, let's say there's 100 entries. Classically, it would take you on average 50 tries to find it. With a quantum computer, it takes you 10 tries to find it, right? But the problem is that this is the way this problem is set up is completely incorrect. So you can use Grover's algorithm to do this. Why? Well, because this is a classical list of entries. So this list lives in memory, in some random access memory or some hard disk or whatever, right? If you want to run this list through a quantum computer, you need to turn this into the list itself into a unitary gate.
Yeah.
And to generate that unitary gate, you need to scan the whole list. So you need to run through the whole list and assign different either a 1 or a -1 to each of the entries, and you assign a -1 to the one you're looking for. But you have to scan the list to assign this, right? So Grover's algorithm cannot be used to search through an unstructured classical database faster than a classical algorithm. And this is typically not explained. Now, someone that has spent a little bit more time learning about quantum computer would say, well, no, wait a second. That's not the purpose of Grover's algorithm. What you typically would do for doing this type of search is you take this list and you save it into a quantum random access memory, so a QRAM, right? And you only need to save it once, and then it's already a quantum data, so you can turn it into, an oracle that you can access through Grover's algorithm, and you can reuse it many times. So yes, you have to scan the whole list, but only once, and then after that you can reuse it. Well, the problem is that up to this day, there is no well-known way to implement a quantum or quantum random access memory, a QRAM. So QRAM is a theoretical block that, yes, you can use to expedite algorithms with pen and paper, but in the real world, there's no such thing as a QRAM gate. So, the thing is, okay, if you're going to present Grover's algorithm as being able to search through an unstructured database, explain it that way, right? Explain the limitations, and this is not typically done. Now, that doesn't mean that there is no proven advantage for Grover's algorithm. So there are ways in which you can use Grover's algorithm to get a square root of n speed up. For example, I think the most famous example is something known as circuit SAT, or a circuit satisfiability problem, where what you do is, if you have a digital circuit and you want to find out if that circuit gives you as an output, let's say a 1 or a 0, or you want to find out if it satisfies certain condition, a certain equation. Well, there is a way to turn that digital circuit into a quantum circuit in polynomial time. So you can do this efficiently and run it through Grover's algorithm to get the answer faster than you can do classically. Classically, you will need to run all possible inputs to that circuit to see if the output turns into a 1 or not. You're trying to figure out, does this circuit give me a 1 for any possible input? So you need to try all inputs, or on average, half of the inputs. Well, for Grover's algorithm, here you don't need to pass a whole list of elements. You need to pass the circuit itself. So that can be done efficiently. So, but then the problem is that this is not explained like that, right? Grover's is presented as something that can be used to expedite all sorts of different problems that probably don't see a speed up. So that's a basic example, but as you keep increasing the complexity of the algorithms, there's more and more misconceptions that are typically not presented. Another example is, this is a little different, but Shor's algorithm, you can see over the news that quantum computers have factorized a number this size, right? The reality is that Shor's algorithm has never been used to factorize any number. There's no demonstration of Shor's algorithm factorizing anything. Now, there's a typical, there's a famous example that I think it factorized the number 21 or something like that. But that's not true. Even for very, very small numbers, this has not been demonstrated. The way this was done is by knowing the number. So Shor's algorithm is more than just a quantum algorithm. It has a big portion of it is classical computation, right? The quantum portion of it performs something known as period finding. So to factorize even the smaller numbers that have been said to have been factorized, they knew the period ahead of time, and they modify the circuit in Shor's algorithm, knowing this information, to show the factorization. But then, in that case, you don't need Shor's algorithm if you already knew the period, right? So, of course, I'm not saying these are not impressive demonstrations. Showing that a quantum computer can run this type of circuits and give you, the right answer is very impressive, of course. But, when it's publicized and, a lot of news outlets pick up on these stories, it's presented as if it's been done in the way that is intended to be used, but it's not. It has all these different simplifications that ultimately you don't want to have to use when you really have to implement Shor's algorithm to, let's say, factorize a number with more than 1,000 digits or 2,000 digits, right? So, that's another level of misconception that people are like, oh, Shor's has been already demonstrated in real hardware. That's not true, right? And it just keeps going on. You take, for example, the HHL algorithm, which is the one that really motivated people to start looking into quantum machine learning, right? The way it's usually presented, it makes people think that you can solve a linear system of equations exponentially faster than what you can do classically. And that is very far from the truth. What happens with HHL is that you're trying to solve an equation, right, where you have an output vector and some matrix, and you want to find the input vector that solves that equation, right? So, a vector V equals a matrix A times a vector, X, whatever, right? You're trying to find X. To do this classically, you need to do this matrix inversion. It's very expensive. So the quantum algorithm does this, assuming that the input and output vectors are already quantum states. But to turn the classical information into quantum information is extremely expensive. It's very hard to do. So you lose all of the advantage that you would get from the algorithm when you try to do this on a quantum computer. Again, similar to the example with Grover, this doesn't mean there's not a place where HHL can give you practical advantage, but it's very, very limited. First of all, you can't get the output vector unless you perform state tomography, which is really expensive. But you can think of certain problems where you're not interested maybe in the output vector, but on properties of the output vector. So measuring some expectation value of something interesting that that it's encoded in the problem. But the way it's typically presented is I have this linear system of equations here in the classical world, and I have it here in the quantum world. This gives you exponential speed up compared to this one, assuming the same level of input and output, and that's not true, right? And that I think leads to many of the other more complex misconceptions that there are. So, in QML, quantum machine learning, there's so many misunderstandings on what can be accomplished, and they usually have to do with what I just described for HHL, is that people are taking these algorithms to using the assumption that classical input comes in, classical output comes out, and that's not the case. Yeah. You need to encode that into quantum data and then take the quantum data back into the classical domain, and those two processes are very expensive. So, in the space of quantum machine learning, I think there's way too many claims that there's potential speed ups, and this just is not true. And a nice example of this is, I think maybe a year or 2 years ago, there was this paper from some of the members of the Penny Lane group in Xanadu, where they took, I don't know, maybe 50 to 60 different papers that had some level of demonstration of a quantum machine learning algorithm, and I think over 100 or 200 databases. And they rerun all of these different models on these data sets that had claimed some level of advantage. And what they found out is that I think 0 of them demonstrated any performance improvement over a classical algorithm. And they took it one step further, which I thought it was very interesting. So what they did is they took the models they had and they removed some of the entanglement that would happen within the circuit. And, one of the advantages of quantum computing is that it allows you to explore a much larger space than what you can do classically. So if you remove entanglement between the qubits, you're basically just running a classical model. And what they showed is that in a lot of these demonstrations, when you remove the entanglement, the results improved compared to the ones that had the entanglement gates in them, showing that it's not the quantum that is really helping you here. There's some other something else going on that might be giving you a better result, but it has nothing to do with quantum computing. And this is similar to an announcement that was made a few months ago from IBM and what's the name of that bank? HBSC, the Hong Kong Shanghai Bank.
Yeah.
Where they claimed, and this was all over the news.
They
claimed, yeah. They claimed that their quantum model gave a 34% improvement in the classification of some data. So all the news outlets were like, quantum computing demonstrates, and this was run on real hardware. And then you go and read the abstract, and just in the abstract, it clearly says that they see a 34% improvement compared to classical approaches and the simulation of their quantum approach. So they say running it in real hardware adds noise, and this noise is what's giving us this 34% improvement compared to. I mean, that doesn't make any sense. How it and then the problem is that there's no explanation on why this happened. There's a line there. If you keep reading the paper, they say it's this is interesting. So is it would be worth exploring why this is the case. But I mean, that that's just a claim of having a quantum computer giving you a better response where there was nothing related to the quantum part of the quantum computer that gave you the improvement, right? So, and yeah, you just see this all over the place. There was a paper published, I think, say yesterday or 2 days ago, on all on different quantum machine learning models for time series calculations, showing they were benchmarking the quantum models with classical models. And again, similar to the Penny Lane paper, they just took some
Yeah.
percentage results and they showed there's absolutely no advantage on the quantum side compared to classical. So I mean, I see this as a problem because, yeah, I'm not discarding that there is a lot of work that goes into building these models, running these models, trying to understand how they work. And there's a lot of smart people working on all these things. But the way these results are typically presented are, trying to claim something that's not happening, something that's not been demonstrated, right? So I find issue with that, and I think it's not good for the field overall to do things. Yeah. So, but again, I'm very optimistic, especially on the side of quantum simulation. I think that there is a lot of potential there. But again, this claims of quantum computing is going to solve global warming. I mean, that's just very exaggerated. So let's take it one step at a time. Let's keep trying to use it to solve this more simple, maybe not practical models, and keep improving the hardware to get to something of practical use. And the key for that, I think, is definitely quantum error correction, which I think most companies finally are taking it very seriously.
I also believe that most people per se are more fascinated or fancy in general the mechanics behind the technology. But what they fail to maybe see or rather neglect really is the things that the theory, the mechanics posits that quantum nature or quantum behavior can do. It does not really translate completely into reality. Like quantum tunneling is a thing, teleportation is a thing, superposition, entanglement, they all sound, they posit these fancy descriptions of what reality can be, right?
Hmm.
You can teleport, you can time travel, so on and so forth, all these fancy different things. But that is not what the reality, the real commodity of quantum computation or quantum technology currently is able to deliver. And it is even more testament then to the fact that quantum technology is not a commodity for either business bettering it or making it more efficient is a completely different say. But even just an ancillary aspect of any sort of business operation per se, like any enterprise grade solution right now at least, if it is, you really don't know, as you said, that the results are generally from the noise or the classical aspects of the quantum architectures as well. There may be
Mhm.
some hybrid solutions that give some sort of value or result, but not to the extent where you have this some consumer grade or enterprise grade product that you can productize based off of quantum nature per se. I think that
Yeah.
is actually the junction.
So, and so the thing is that I was part of a startup company at one point, and something that is very important is to stay optimistic and to set goals that are that push the technology to the next level. So, claiming that eventually your company will be capable of achieving something great, I think it's important, and it's good to you know have this idea that that this technology can do a lot more than what we know today, right? I mean, it was clear in the case of machine learning and AI, since most of the results are heuristic, that once you have a working computer or working technology, you'll be able to discover things that you even didn't think of, right? But I don't think that should come at the expense of blatantly lying about what can be done, because there are things that we know cannot be accomplished using quantum computing. And some people exaggerate things to the point where that they're saying things that are just not true. And yeah, I have some examples, but maybe we leave that for another separate discussion. Yeah.
Yes, certainly. I mean, there are various avenues, from biology to in general, playing with magnetic fields to, as you pointed out, simulations, so much and so forth, with the entire aspect of how you can harness the science of quantum. But as you said, that should not come at the expense of, blatantly lying out to what
Yeah.
the technology is capable of currently.
Mhm.
But yeah, moving on to sort of the final aspect. I mean, we touched upon it briefly, but your three key pointers per se, you can raise the number if you want, but like sort of this actionable checklist for the younger folks in their respective careers or studies that they can sort of imbibe in terms of how they can go on to become better engineers and scientists and thinkers.
Yeah, I mean, um, I yeah, as I mentioned, I think that trying to pursue something you're passionate about is very important, and being flexible if that path doesn't look exactly the way you were expecting, and also adjusting as the opportunities or the market of opportunities changes. Try to be able to pivot. So yeah, those are three things that I think are key. And the other thing that I think, at least for me personally, was very important is, you hear a lot of interviews where interviews with people that are very accomplished and have a great level of success, saying, when I was young, I had this professor or teacher in high school that was really influential for me and made me think in a different way. And at least in my case, unfortunately, I never had something like that. I had the privilege of going to a really good school growing up, but it was a very linear or very unidimensional place. So basically, you were given, let's say, in my math classes, I was terrible at math. I found it tedious, and it was, this is the equation, solve it, factorize it. There was no rhyme or reason for why I had to do that. And I mentioned earlier that I started learning about physics, and that kind of motivated me because I saw a little bit more of the practical aspect of things. But there wasn't really a moment where I was like, oh, this is life changing. This person is really, shaping me to be, the next part of the next generation of thinkers and so on. So where I'm going with this is that if you don't have that in your life, don't feel frustrated. Not everybody has that privilege. What really changed, I would say, really changed my life was the internet. I was lucky enough that I was the internet came into my hometown when I was at an age where I was very curious. So this was maybe I was 13, 14 years old, and before that there was no internet, and books were limited, and especially in my hometown, you couldn't go and pick up any book you wanted. So when the internet came, it opened the door to this world of possibilities, right? And a lot of the things I learned were just by going online, searching for things, and find inspiration on maybe not people that are in your everyday life, but that there's a lot of place to find inspiring and interesting things. So in my case, I had no experience programming or with computers, and one day someone in my class was like, oh, it would be cool if we had like a class website. So I just went online and I started just inspecting internet sites and looking at the HTML code, and I just said, okay, I'm gonna do this. This seems fun. It seems interesting, and I just found inspiration in that, right? On the physics side, I remember we started learning about in school about forces, and there is like the electromagnetic. There's the electrical force and the magnetic force, and then there's this gravitational force. And I got curious about that, and I went online and I found this website, which a few years ago I was curious, and I went, and it's still up. It's called The Particle Adventure, and it's I don't know if it's designed for kids, but it's very simple, and it guides you step by step on all the different aspects of the standard model of physics. And I just that really changed my way of looking at things. This very simple, this was in 1997, I don't know, 1998 maybe. And just being curious and looking things on your own and trying to find inspiration on anywhere you go or anything you see, you try to get the most out of it, right? So yeah, I mean, if for some reason you get frustrated because you hear all these people saying, I had this aha moment, and this part of my life that changed me. um, don't feel that you can't accomplish things if you don't have that. Try to pursue it, try to find it, and there's many different places to do this. So and in many cases it can be luck, but you're in control of your life, right? So try to find it, right? Do your best, and um,
Even though I think you talked about it enough, like sufficiently so and satiatingly at that. Um, Still, as a tradition on the show, Dr. Diego, what would be your word to humanity at large?
oh wow. My word to humanity. Um, I think um, I just mentioned how I found the internet to be such an inspiring place as a young person. I think with social media, um, we've come to a point where it's very easy to be, um, I wouldn't necessarily say rude, but
Mm,
come up as dismissive, or if someone has an opinion you don't agree with, just not be polite about it. I think my message to the world is, you know try to see every situation, every interaction you have, as if you were having it with someone in person, and try to be kind, be polite. Remember that everybody has a different background, and uh, you know a lot of people might have misconceptions about things that they've been told, and they might be incorrect. Try to be um, careful with the way you try to correct someone. I think it's important to um, try to do our best to, especially online, because as I said, there's a level
mm,
of disengagement, right? That turns people into something they're not. So, and I think that causes more harm than good. Like if you're trying to tell someone, "Hey, you're wrong for this and this reason," if you come in too strong and you try to tell them that, you know, "Hey, you're completely wrong. What are you doing? You're spreading misinformation." I think a lot of people react that in a negative way as well.
mm.
So that it won't help in trying to change people's minds when you're not being, you know, kind and compassionate, and try to keep in mind that we all have our own way of thinking, and our own preconceptions, and that if we want to improve the the way we're right about things, we need to be careful how we deliver the message. Maybe I'm not taking my own advice. I just went on and on about how bad quantum computing is in delivering messages, and but yeah, I try my best to
No,
not
you
not
did
make
take up
too.
your advice. You were kind, you were considerate, careful. I mean, yeah. But yes, indeed. I think there is this definitely this level of or degree of detachment, as you said, disengagement when you are conversing with people online. Surely there's this aspect of connection where you're able to be a part of this entire mesh. with different nodes that represent different people all across the globe, interconnected through and through. But at a personal level, somewhere you know that okay, it's maybe just another entity behind the screen, which becomes even more, atypical with the advent of AI agents and bots, more infiltrating more and more this layer of mesh. But still, never hurts to be cognizant that okay, there might be an individual, living, breathing individual, like the friend that I just chatted with, like the sister who I just talked to over the phone, or X and Y person who I care about. I can be a little more cognizant about what I say, how I say it. So yeah,
Yeah.
Dr. Diego,
So yeah,
thank you.
I also try to take my own advice when I can. It's not always easy, but yeah, I hope that we can all together have a little bit more understanding of each other, because ultimately what we want is to, converge to a point where what what we have is actual truth, and the right answers to certain questions. So yeah, okay. Well, thank you so much.
Dr. Diego, thank you so much for doing this. I really appreciate it. It was
Yeah, no,
delightful to have you over the show. Like, thank you so very much.
all right. Have a great day.
Okay, so